All right, welcome to my lecture on section 8.1 on sequences. And a sequence is basically just an infinite list of numbers written in a certain order. So this a sub 1, a sub 2, a sub 3, those are real numbers. They could be decimal numbers, they could be fractions, they could be whole numbers. And we denote a sequence like this with these curly brackets, and we write a sub n, meaning the n can change from 1, 2, 3. And we also write it with this infinity on top and n equals 1 on the bottom. And this should be reminiscent of what we've seen with summations, like sum from, n equals 1 to infinity of something like that. That's what this notation should remind you of. So if you're given a sequence like this, sometimes you're given it in terms of numbers, sometimes you're given it in terms of a formula. The idea is that you're just plugging in this case, n equals 1, so that would be 1 plus 2 over 1 squared, 3 over 1. So your first entry would be 3. And then you plug in 2, you get 2 plus 2 is 4 over 2 squared is 4, so that comes out to being 1. And then 3 plus 2 is 5, 5 over 9. And then you get, 4 would be 6 over 16, which reduces down to 3/8, etc. And I was simplifying each of the fractions along the way, but sometimes it's actually easier if you don't simplify the fractions, because you can sometimes see the pattern a little bit easier. Right? So if I write it out this way, it's pretty clear that the top numbers are going across, increasing by 1, and the bottom numbers are getting squared. And I could also change this sequence to look like n over n squared plus 2 over n squared, and then simplify that to be 1 over n plus 2 over n squared. And there are going to be times where doing those kind of algebraic manipulations are going to be useful. So in this above example, example 2, I gave you a formula and you had to come up with what the sequence looks like. And for example 3, we're given a sequence and now we have to come up with the formula. So I noticed that a couple of things. The first thing is it's going negative, positive, negative, positive, back and forth. Anytime you see that, it's what we're going to call an alternating sequence. And you can make it alternating by doing a -1 to the n power or to the n plus 1 power. So here, our very first entry, this is our n equals 1, is right there. Maybe I'll change colors to make this a little bit easier. And then n equals 2, n equals 3, n equals 4. So anytime that I have my n being odd, I want it to be negative. And if I do a -1 to an odd power, it's going to give me a -1. If -1 is to an even power, the negatives cancel out and I get a positive. So I start with that, and then I know I'm going to need something that's a fraction. My top numbers are going 1, 4, 9, 16, 25. That looks like an n squared. And you want to be careful with this. We know that it starts at n equals 1, and then n equals 2, so 2 squared is 4, 3 squared is 9. Sometimes it'll be off by a little bit, and you might have to put like a n plus 1 quantity squared or n minus 1 quantity squared. So just be careful about that. And then on the bottom here, it looks like we're doubling each time. So 2, 4, 8, 16, 32. That's like a 2 raised to the n power, because each time I increase I'm multiplying by another 2. And that looks like my formula, going to infinity, starting at n equals 1. And I can check, if I plug n equals 1 in here, I get -1 to the n times 1 squared over 2 to the 1, which does in fact come out to -1/2. And if I check for n equals 2, n equals 3, etc., it will come out to give me the right thing. So for the next one, exercise 4, I want you to go ahead and pause the video for a moment and try to figure out the answer for exercise 4. When you're done or you're stuck, unpause the video and you can see my answer. Okay, hopefully you have worked on this one. The big thing to notice for this one is that we're changing each time whether our n is positive or negative. So this is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. Anytime that n is an odd number, we're just getting the number 1. And anytime we have an even number, we're getting 1 divided by that even number. So this is going to end up looking like a split function. So our sequence, in this case, is defined to be, I would write it this way, a sub n equals, a sub n, let me put it this way, where a sub n equals, and I'm going to make a split definition, 1 if n is odd, and 1 over n if n is even. And this is sort of a strange definition, but it is a legitimate way of defining a sequence, because for every single n value, that's what you get. And if you wrote this out in words or something like that, that's also a perfectly legitimate way of doing it. All right. Next, let's look at some sequences that don't have very easy or simple formulas. The first one we're going to look at is what's called a recursive sequence. So in this one, you're given a starting point and a rule for how you get the next thing. And then from that, you can basically build the entire sequence. So it says find the first 6 terms in the sequence defined by a sub 1 equals 5. That's my first entry. And a sub n plus 1 is 2 times the previous number minus 4. So if I want a sub 2, that's going to be 2a sub 1 minus 4. My a sub 1 is 5, so 2 times 5 is 10, minus 4 is 6. And then my a sub 3 is going to be 2a sub 2 minus 4. 2 times 6 is 12, minus 4 is 8. A sub 4 equals 2 times a sub 3 minus 4. That's 16 minus 4 is 12. And then 12 times 2 is 24. Minus 4 is 20. 20 times 2 is 40. Minus 4 is 36. That wasn't supposed to happen. And it'll keep going on like that. So I can write my sequence in that way. And one thing to notice about this, there's other ways you could describe this. Like from 5 to 6, it increases by 1. From 6 to 8 increases by 2. 8 to 12 increases by 4. So each time that it changes to the next number in the sequence, the difference between the sequence numbers is doubling. And then the Fibonacci sequence is another famous one. It's 1, 1, 2, 3, 5, 8, 13, 21, etc., where you take the 2 previous numbers and add them together to get your next number. So recursively, this is a sub 1 equals 1, a sub 2 equals 1, and then a sub n plus 2 is equal to a sub n plus a sub n plus 1. So I would define my first 2 numbers in the Fibonacci sequence, and then my next number is defined by adding the 2 previous numbers. And then last of all, we've got some really weird sequences. So think for a moment what might be the rule for this sequence, 3, 1, 4, 1, 5, 9. If it's not coming to you, think of what would happen if I put a decimal place in between that 3 and that 1. Does that look familiar? It should. It's the first few, I guess, decimal numbers in the decimal expansion of pi. So the rule here is a sub n is equal to the nth decimal number in pi. And that might not actually be true because I guess my n equals 1 is going to be my whole number. So n equals 2 is actually the first decimal number. So if I wanted to be completely precise here, I would say it's the n minus 1th decimal number in pi. And there's probably better ways of describing that so that other people would understand it. But we'll leave it at that for now. So we're going to talk a little bit about convergence and limits of sequences, and then I'll end this this particular video. So we often want to know if a sequence will converge or diverge, and what their limit is if one exists. So we want to know if this sequence is going towards something. And a sequence has a limit L if we can make the terms a sub n as close to L as we like by taking n sufficiently large. So we write the limit as n goes to infinity of a sub n equals L, or a sub n approaches L as n approaches infinity. And if that L exists, we say that this particular sequence converges and has the limit L. If not, we say that the limit diverges. And this should look familiar to you because it's basically the same definition we had, or it looks very similar to the definition we had for a function having a limit. And notice that the terms as close as we like and sufficiently large are not very precise. So we could do some examples to illustrate what the definition means. So this particular sequence, a sub n equals 1 over n, converges to 0. And if I wanted to make sense out of as close as we like and sufficiently large, I could say find n such that a sub n is within 0.001 of the value 0. In other words, I want my a sub n to equal 0.001 or be less than that. And yeah, really I want that 0.001 to be greater than my 1 over n. And if I multiply the n to the other side and divide the 0.01 over, I end up getting that n is greater than, that's 3 decimal places, 1,000. So what this means is that for any n value greater than 1,000, my sequence is going to be giving me a value less than 0.01, which is within 0.01 of the number 0. So as close as we like here, that means this thing right here. I'm choosing some number as close to my limit of 0 as I want. I could have chosen 0.0000001 and done this same calculation, and I would have found an n value sufficiently big that anything over that would be getting me within this value that I want. So as close as we like and sufficiently large are things we can make precise.